So we want to be able to make the connection between rational function graphs, key features, and the equations. So a quick reminder about what we talked about previously. You've got your rational functions, and we think about it as the parent function, and we've got different transformations that can happen to it. And as in our previous lessons, we talked about the positions of the parts of the function and how it controlled the graph. And we said that things in the numerator in place of a, that controls the vertical stretch or shrink of the graph. So if a is greater than 1, it's faster, so it's stretching it. If it's between 0 and 1, it's slower than it was before, so it's a shrink. And we know if a is less than 0, if it's a negative number, it's a reflection over the x-axis. B, that's an input change. That's going to change how it's horizontally moving, so a shifting left or right. So remember, if you see an x minus b, it's actually moving it the inverse of what you think it is to the right b units. If you see x plus b, again, the inverse of what you think, it's moving to the left b units. The c value is another vertical on output change, shifting of the graph. So it's going to either move it up or down. So we see a plus c, it's going up that many units, minus c going down that many units. So input changes are with the x's, so b, output changes would be your a and c. Again, the parent function we referenced, 1 over x. We have our table that we use for the parent function to build our transformations, whether they're input changes or output changes. We know with our rational functions we do have some problems show up with some asymptotes. We know that we cannot divide by 0, so we have x that's being an input, so we cannot use that input of 0, so we have a vertical asymptote. And then for outputs, we know that we'll never have an output of 0 because every number that we put in for x is just going to get smaller and smaller and smaller, but never equal 0. So it's going to approach it, but not touch it. So it's how we're getting our horizontal asymptote here. That affects our domain and range. Remember, domain looks as the left to the right, the inputs. So again, we're going from negative infinity up until 0. We cannot include it because of the asymptote, but when everything is greater than 0, we can use it. So remember, we're joining the two pieces of the domain together, putting them in union. It's talking about all the inputs possible for your graph. The range, the outputs, okay? So we're looking vertically, how low to how high. So again, this would continue going down. So we can go from negative infinity up until we get to 0. But everything greater than 0 to positive infinity works as an output. So again, we're putting in union the two pieces that make up our range. So this is our parent function for the rational, and we always want to keep that in mind when we're looking at the equations and graphs. So if we go back to our original problem, we were talking about trying to match the equation to the graph. So the first things I would look at would be the asymptotes. And so remember where the original parent function is. The asymptotes are both at y equals 0 and x equals 0. So I'm going to plot those on my picture to have me think about what's changing. And I put the kind of template for the equation here. Now we can see normally that vertical asymptote is at 0, but it's now moved to the left 1 unit. The horizontal asymptote is usually at 0, but now it went up to 2. So again, if we think about those movements and where they play into the equation, that would help us. So again, we said vertical asymptotes going to the left. That's an input change. That would go here with B. And moving up the horizontal, that would go with the C change. So let's see. Based on these movements, can we start matching to any of our equations? Well, we don't necessarily have the plus C at the back, so let's focus on the B value here to see how it's moving. So again, moving to the left, we said it's the inverse of what you think. So we should think about this as going to the left, which is the x plus 1. So all the other options that don't have x plus 1, we're going to eliminate. So that means A and D would not be answer options. Now, because I don't have a C being written here, we're going to have to hold off on eliminating the other ones. Let's think about what are some other key features in the graph that we usually look for. We've got asymptotes, then we also look for intercepts. In particular, I'm going to go with the y-intercept because I can read that from my graph, and it's very helpful in my equation. So here's my y-intercept at 0, 6. y-intercepts always have an input of 0. So if I put 0 into my remaining equations, in order for it to represent this graph, I'd have to have an output of 6. So let's test them and see what happens. If I take the input of 0 into that first equation here for b, what will we get out? A 0. I'm supposed to get a 6. That's not working, so b can't work. Let's do the same for the next two. Again, we're going to put 0 into the function and see what we get out. So by doing so, if I put 0 into this one, I'll end up with 6 over 1, which is 6. If I put 0 into this one, I'll have negative 6 over 1, which is negative 6. Again, it's got to match 6. So we already eliminated b. What gives us a positive 6? C. So that would be the equation to represent the function that's shown. And that would be the strategy I would suggest doing. Now, if you did have two answer options that gave you the output of 6, then I would go and check and see, can you use an x-intercept perhaps to help you narrow down your choices.